So the last topic on parallel plate waveguides that we will talk about is the idea of phase velocity and group velocity, right? So now that we have these entities called modes rather than plane waves, let us try to describe certain important movements, right, of energy, of electromagnetic energy in the context of modes, right? So here I basically have, let's call this black line as a representation for the direction of the k vector of a plane wave, right? And this is the transverse plane containing E and H. Okay. So the red line indicates the direction of propagation. Okay. So remember that I can picture the modes, right, in a parallel plate waveguide as essentially the summation of two plane waves in an unbounded media, but the angle or their directions are very carefully chosen based on the frequency of electromagnetic radiation and the distance between the parallel plate. Okay. Now we have a few different couple of definitions, right, of something that is happening over time. So the black dot, right, is just a fixed point, right, on this uh, plane of constant phase, right. So we have the blue line representing the constant phase plane, right, and the black dot and the blue dot are always going to be on this plane of constant phase, right, whereas the blue dot is restricted to be on the line, right, shown by the direction of propagation, right. So it is essentially the intersection of the plane of constant phase and the direction of propagation, and that intersection point will move to the right. Okay, as the black dot in time moves along the k vector representing the movement of the wave front, right. So I can call the blue also as the wave front. So as the wave front is moving in the direction of k, right, we will notice two specific points, right. One is the intersection of the wave front with the direction of propagation, and also the projection, right, of how much the black dot has really moved along the direction of propagation. Okay. So the red dot is how much the black dot moved, right, along the direction of propagation. Okay. So let us just play this animation. Okay, so let us call these points A, B, and C. Okay. Okay, so the points were somewhere here, here, and here. Okay, so B has moved to the new location B prime, this is my C prime and A prime. Okay. So the figure of course is to scale, right? So I can clearly see that B prime is less than A prime, which is less than C prime. Okay, just a geometrical construct, right? Okay, so we are going to associate phase velocity okay with the movement of the blue dot, right? Phase velocity is the speed of the blue dot. Okay, and B prime, right, is what we call the group velocity. Okay, of course A prime is nothing but the velocity of a plane wave. Right, in a dielectric medium, right? So A prime is, so if I were to clock this, say that this movie ran for some time t, right? So A prime would essentially be V1 times t, right? We are going to say that BB prime is something called Vg, standing for group velocity, right? And CC prime we are going to say is the phase velocity. Okay. So the red dot in some sense is also the indication of how the energy is flowing in the waveguide, right? So if I were to take E cross H, that is going to be in the direction of K, and then if I dot it with the direction of propagation to know the net power flow going along the direction of propagation within the waveguide, I'll actually essentially understand that the movement of BB prime, right, by the red dot is essentially an indication of the rate at which the power is flowing in the waveguide, right? And that is essentially what we call the group velocity. Right, and you can say that the phase velocity is essentially the intersection of the phase front with the direction of propagation. That intersection point, how is it moving in time, right? So it is quite obvious to see that the phase velocity is actually greater than the velocity in the medium, right? So we can say Vg is less than V1, is less than Vp. Okay, but this should cause no alarm, right? That the phase velocity is greater than the speed of light, right? It is not just a mere construct, right, of geometry that allows for points to move at greater than speeds of light, right? It is not to say that information or energy flow is traveling faster than the speed of light. In fact, it is not. It is moving at what we call as the group velocity, which is less than the speed of light always, right? So regardless of how you choose to orient this k vector with respect to the direction of propagation, you can confirm this fact, right? So for example, let's take an extreme scenario, right? Two extreme scenarios where the k vector is lined up with the direction of propagation. In that case, all three velocities are the same, right? So A, B, C would become coincidental points, and you'll notice that the points move together, right, along with the velocity of the plane wave. And the other extreme case is when the k vector is perpendicular to the direction of propagation, right? So in that case, the phase front, right, is actually parallel to the direction of propagation, and you'll notice that the phase velocity is infinite, right? And whereas the group velocity is 0, right? So the wave is just bouncing back and forth between the two parallel plates, and it's not really going anywhere, right? Okay, so let us try to get the expressions for phase and group velocity. Now that we have understood what they mean, let us try to get some expressions for them. Okay. So the phase velocity Vp is quite simply omega by kxi, right? So remember that your E total was proportional to e to the minus j kxix, right? So this kxi is essentially the phase constant of propagation, right? Right. So I can define an omega over kxi, right, which we find out to be as the same as the phase velocity, right? So remember what was kxi? It was k1 sine theta. Let us think through that, right? So I remember my perfect conductor and my k vector. And this was my theta, right? So k cos theta would be kz. So k1 cos theta I and kxi is k1 sine theta I. Okay. So we know for the parallel plate that cos theta I is very specific, right? So cos theta I is m lambda 1 over 2d, right? Which means that sine theta is square root of 1 minus m lambda 1 by 2d whole square. Also, let's remember that 2d by m is lambda cutoff, lambda c, right? And fc is essentially v1 by lambda c. Okay, so these are all expressions that we got prior. So what does Vp become? Our phase velocity is essentially omega over kxi, which is k1 sine theta, which is square root of 1 minus m lambda 1 by 2d, but 2d by m is lambda c, so I'm going to write this as lambda 1 by lambda c whole square. Okay, this is also equal to omega by k1 square root of 1 minus fc by f whole square. Okay, so lambda and f are inversely related, so the cutoff frequency goes up, right? Right, let's not forget omega is 2 pi f, k1 is omega square root of mu1 epsilon 1. So don't forget all these relations, okay? But the interesting thing is, remember that the velocity of a plane wave in an unbounded dielectric medium, right, which was isotropic and homogeneous, we saw that the phase velocity was constant, right? It was just omega by k, right, and it was not a function of frequency. Now we find that Vp is a function of frequency. Okay, so this is what we call as a dispersive medium. Right. Remember, the dielectric has suddenly not become dispersive. Right. The movement of electromagnetic fields within a bounded medium, right, is a it is a dielectric that is bounded by perfect conductors on two parallel planes, right? And the movement of electromagnetic fields in such a scenario, right, shows that the velocities are now functions of frequency, depends on the electromagnetic frequency, right? So this is also called as waveguide dispersion. Even though the material is not dispersive, the construct of putting two parallel plates or two conductors around a dielectric medium and forcing electromagnetic fields to flow between these two plates makes the fields move in a way that their velocities are now functions of frequency, right? So what can we say about the group velocity? Okay, so let us go back to our picture in the previous slide. Remember that this was my k direction, right? This was my A prime, and then I had my B prime. Okay, so remember that my angle of incidence is between these two, right? Again, this was the picture we had. Actually, what would be easier is if we started at the intersection. Okay. Okay, let's say that A, B, and C all started off at the intersection. Okay, and after some time t, we notice that A moved to A prime, B moved to B prime, and C moved to C prime, right? So if this is your 90 minus theta. Okay, and let's say that this is some delta S. Okay, so we notice that C prime is essentially delta S by sine theta. Okay, okay, and BB prime is delta S sine theta. Right. So if I did C prime by delta t, I actually get delta S by delta t 1 over sine theta. Okay, so this is Vp, this is V1. Similarly, we have Bb prime by delta t is delta S by delta t times sine theta, right? So of course we are seeing the same thing here, right? So omega by k1 can be written as v1, right? That is the speed of the electromagnetic wave, and sine theta is square root of 1 minus fc by f the whole squared. So we notice that this relation corroborates with this. Okay, so v1 by sine theta. So similarly for V group, we have this as v1 sine theta, which is v1 times square root of okay. So we get expressions for the phase and group velocity. Okay, so let us finish with a very simple parting comment for group velocity. Group velocity is actually the physical movement of a point on the wavefront in the direction of propagation. Okay. All right. So let us continue from here about rectangular waveguides.